On the screen is the Analog Discovery Network Analyzer, and we'll talk a little bit about the circuit that we're running at this point. Oh, sorry, I bumped it. At the top you see the gain of this particular amplifier, and at the bottom the phase, and you see it's going from 100 kilohertz it's going from 100 hertz to a megahertz, and you see that at around 100 kilohertz the gain begins to fall off and the phase begins to change. Now, like I say, I'll show you the circuit in a minute, but what we are going to try to illustrate here is another of the projects from the Art of Electronics lab manual and the use of the analog discovery. Specifically, what we're going to be talking about is, I bumped it again, is the relationship between frequency response and another characteristic of amplifiers, particularly operational amplifiers, called slew rate. So in a minute we will look at all of that, but in the meantime I also want to cover a small point of, well, it's a little bit of a pet peeve of mine about the way that people talk about operational amplifiers. So let me turn to that first, and then we'll come back and look at the circuit, and then we'll measure the slew rate and compare it to the frequency response. I have to warn you, the following material may not be suitable for children or for adults who think like children in the lab. Folks, Gandalf does not exist, except in the movies and in some very nice books by Tolkien. In other words, there is no wizard. What do I mean by that? When describing operational amplifiers, I have seen more than one, and in my opinion way too many, people who try to describe the way an operational amplifier works in terms of a virtual ground here that is somehow under the control of a wizard within the operational amplifier. And as the story they give is, the operational amplifier tries to maintain a virtual ground at this point, and the little wizard looks at the output and looks at the input and adjusts this point until the output and the input are in the relationship of this voltage gain equation. Well, if you want to think of it that way, that's fine, but in reality it's just Ohm's law. And Ohm is not the name of a wizard. Let me show you what I mean. If you redraw that circuit like this, and sometimes a change of point of view can give you some insight. If you think of the feedback resistor and the input resistor as just a resistive divider, so that this node voltage is just the Ohm's law value determined by Vout and Vn. Now Vn we're going to assume at this point is fixed, or at least is not under our control. We're also going to assume for purposes of this that the open loop gain of this op amp is 50,000. Now there are a lot higher values than that. 100,000 is more typical today, but I'm using 50,000 because that was a typical value for a 741 back in the early days, and I'm going to be using an early 741 later when I talk about slew rate, so I'm going to stick with this one. So let's do a little calculation of the values. Let's assume that Vn is 1 volt. What, what you would think is, well, if you have the equation of RF over RN, that means that the output, if this resistor is 10 times this resistor, then this overall stage will have a closed loop gain of 10. The output voltage will be 10 volts. But that's not actually what's happening. The voltage here is really the Ohm's law equivalent of the output voltage and the input voltage, where the output voltage is just the open loop gain of the amplifier multiplied by the node voltage. So what does that mean? Well, what that means is that this voltage is not really 10 volts. It's really 10.0002. Why is that? Because this 2 microvolts or 200 microvolts multiplied by the 50,000 gain produces the 10 volt signal. In other words, the Vn is the sum of, or the Ohm's law equivalent of, this output voltage and the input voltage. In other words, there's 11 volts across here. But this node voltage is not going to be 0. It's going to be 0.0002. And when the output voltage is exactly that value, assuming that these are exact resistors, and assuming that the open loop gain of the amplifier is exactly 50,000, then this system will be balanced. Well, what if some of those aren't true? What if the gain is higher? Well, then the amount of voltage needed to cause that roughly 10 volt output goes down. So if the gain here was 100,000, then this would only be 100 microvolts, and so on. So it's just Ohm's law, a simple resistance divider that determines how this stage operates. The gain of the amplifier never changes. Its open loop gain remains its open loop gain forever. Unless, of course, you overstress it, in which case its open loop gain goes to 0, usually when the magic smoke emits. So, if you think in terms of a wizard, that's okay. Like, I enjoy The Hobbit. Loved it as a teenager, love it even today. But Gandalf in the lab is not a good way to look at amplifiers. Instead, try to understand what's really going on. Apply the laws that you know work. In this case, Ohm's law and the open loop gain of this amplifier will tell you what that node voltage is. It's not it's not 0. It's some small amount that, when added to this and after everything is accounted for, multiplied by the open loop gain, produces an output that follows this formula. But it follows this formula only because of a voltage divider effect. Okay, let's move on and talk about slew rate. And so we're back to the Art of Electronics hands-on lab manual, and we're in section 7L.3, as in 7 Lima .3. It's called slew rate. And the circuit we're working with is this circuit. There is a signal in this case it's coming from waveform generator of the analog discovery, and I'm also have channel 1 of the analog discovery connected to that same point, so we can monitor that. A 10K resistor, and then a 741 op-amp that is connected in a simple follower configuration. In other words, it's a unity gain circuit. The output is fed back to the inverting input without any voltage division. And one reason that I mentioned earlier how this happens is, understand that, once again, this node voltage multiplied by the open loop gain of this amplifier is equal to the output voltage. Now, the output voltage will also be influenced by the input. In this case, we have we are feeding the positive input, that is the non-inverting input, through a 10K resistor. So we're not concerned about the actual stage gain here. What we are concerned about is how quickly the output can follow a change in the input. Now, earlier we looked at frequency response, and we got a figure that said that it went out to about 100 kilohertz. I've got a little gnat that seems to want to fly around on my camera. I don't know if you can see it or not, but I can. Anyway, so let's now take a look at the analog discovery with this configuration. So here is the analog discovery with the wave chin set to a 1 kilohertz sine wave, and up here the top channel, that is the yellow channel, is the input. The blue channel is the output, and it's the same circuit that I was showing at the very beginning of this video the frequency response of. So now what we want to do is we want to look at what is called slew rate. Now, slew rate is how fast the amplifier's output can follow the input. It is related to frequency response, but they're not quite the same thing, because usually there's a compensation capacitor inside a compensated op-amp that limits the slew rate. And slew rate is normally specified in terms of volts per microsecond. So what we're going to do is we're going to go to a square wave on the waveform generator. And I'm now going to pull the scope down to a full screen so you can see this a little better. And we're going to change the time base. First, we're going to go to 10 microseconds per division. Now, remember, this is the input, this is the output. Now notice that the output doesn't follow the input. Instead, it has a slope to it. That's due to the compensation capacitor, and that's called slew rate. So to try to measure the slew rate, what we're going to do is go to 1 microsecond per division. And you see there that we are slewing the amplifier from 3 volts to 1 volt. This is minus 3 volts because I have an offset, but basically the output is going from 3 volts to 1 volt. In other words, a 2 volt change. So that means that each of these divisions is a half a volt. So this is a half a volt, this is a 1 volt change, 1.5 volt, 2 volt change. And this is a microsecond wide, so this is per microsecond. So let's look at the change from this point, which is about minus 2.3 volts. Well, actually, let's look at it a different way. Let's say, how long does it take to get from the 3 volts negative to the 1 volt negative? In other words, how long does it take the total time? Well, there's 1, 2, 3, almost 4 microseconds. And that's roughly the specification. This particular amplifier has a specification of a half, don't know if you can read this very easily, I'll try to make it over here. You see it says slew rate, and this is with a 2K resistor. I have a 2.2K load resistor. It says it's about a half a volt per microsecond. So what it's saying is that for every microsecond, if you look at from this point to this point, that's 1 microsecond, it goes up about a half a volt. And so this is very, very close to the specification. Now I can explain why I use the old 741, and I'll show you the breadboard here in a second. The reason is the older op-amps, like the 741 that I'm using, which was actually produced in the 1970s, had much slower slew rate. And the reason slew rate is important is you can't just look at the frequency response. Instead, you also have to look at the slew rate, particularly if you are swinging the output voltage quite a ways. Now what I'm going to do is, before I show you the breadboard itself, I'm going to lower the power supply voltages That one now is down to 5 volts. And that one is down to 5 volts. And it may not be as obvious, but what you notice is that this anomaly, which, by the way, when you first apply the input, the output actually goes through a bit of a sine wave and then recovers back to the original value and then rises rather sharply. That is common in the amplifiers, and that's because the current source in the amplifier is quickly charging the capacitor. But then it becomes a simple RC time constant from that point till the time it reaches the maximum. Now you notice that now it's taking a little over 4 microseconds to reach the full value. Let me go back now to 10 volts, 10 volt supplies, and I am using external power supplies for this so that I could vary this easier and also so I could go to a higher value than the analog discovery allows me to do so. You see now the slew rate is a bit faster, and that's not uncommon. In other words, the higher the supply voltages, usually the better the slew rate. And this particular amplifier, I think, has a 18 volt, plus and minus 18 volt limit. So I'm running it at about half its limit, about 10 volts, plus and minus 10 volts. So I hope that this is instructive, not only in the how you work with operational amplifiers, but also with how you use the analog discovery to measure some of these things. Now let's take a quick look at the breadboard, and you'll see the antiquated integrated circuit that I'm using. And there it is. Let me turn on some more light. It's right here. This is an old Fairchild UA741 in a metal and ceramic package. They don't even make these anymore. But while the package is superior to the dip packages of today, the chip on the inside is really old school. It has a very low slew rate and a number of other problems that have been at least improved upon in the years since. So I hope using this old dinosaur, I'm not referring to myself, but I could be, helps you to understand that what goes on in an amplifier is an operational amplifier is sometimes determined by some circuit characteristics inside. In this case, the compensation capacitor limits the slew rate. And while you can improve the slew rate slightly by using higher supply voltages, when you reach the limit of the amplifier, of course, you can't push that any further. And there is no way you can do anything about this. In the old days, many amplifiers had an external compensation capacitor. And where you needed high slew rate, you could play with that compensation capacitor. Well, in the 741, you can't. It's inside. Once again, I hope this has been at least a little bit instructive. More importantly, I hope that it challenges you to get into the lab and make some measurements. The one thing that I have found, I've said in previous videos, the best engineers are the ones who not only can do the math in class, but they also can do the circuits in the lab. So get in the lab, play around, do some measurements, calculate some things, think about them. And if you want to think about wizards, that's fine, but their place probably is on the theater screen, not in the lab. So in the meantime, look forward to some more videos and have a nice day.